Alrighty. Howdy, folks. So let's look at chapter 4, section 5. And this is comparing alternatives. And there's another method that we are going to learn. It's called capitalized worth. If you are feeling that, man, what's up with all these methods, man? Uh, you are right, but unfortunately, there is nothing you or I can do about it. Apparently, people use all these kinds of things in the real world. So let's go ahead and learn what we need to learn. But then you will see that there is a good reason why they have to introduce capitalized worth. Let me see if I can demonstrate that to you. A capitalized worth for an investment is the present worth equivalent of an infinitely long series of cash flows, right? Okay, let's see. What is this capitalized worth thing? It's a present worth. So you can imagine the cash flow, there's a cost here after 1 year, 2 years, 7 years, all kinds of things like that. Oh, I don't care, man. Just tell me all of that stuff that's going to happen in future. What is its present cost for me so that I can make a decision about whether or not to take up this project, right? And okay, then the big question, after we have done all of that stuff, we started with present worth. Then what's up with this stupid capitalized worth? Why do I need to learn this? The reason is, what if this process is infinitely long? What? How could there be any infinitely long? Obviously, when we say infinite, it is not quite infinite, but for a very, very, very long period. The hope is that it is actually infinite. Ooh, ooh. I cannot think of anything that would last infinite long. Okay, good. How about this? Um, the Capitol building in Washington, D.C., or Lincoln Memorial. Take something historic like that, right? Wouldn't you want that to just last for a very, very long time? Pyramids, 3,000 years ago or whatever, right? Now we relish that. Now the only problem is, if only all different kinds of structures like that had an would live for infinite period, that would be awesome. So there are actually cases where we could talk about infinitely long series. And so the question is, how do we analyze those? And a capitalized worth is one such way. Okay. So in case of projects like bridges, tunnels, highways, hydroelectric dams, and also in the case of endowment funds, we can assume that there would be a uniform series of cash flows for a very long time. That makes sense, right? You don't want to build a bridge that will collapse in 2 years, 100, maybe 200, maybe even forever. That's the idea. And a tunnel, boy, once you bore a tunnel through a hill or a mountain, you just want that tunnel to be used forever. Cool. All right, for this analysis, we need to clearly understand how to deal with infinitely long costs. Okay, case one. If the costs occur every year for perpetuity as shown below, that's the case. What am I showing here? As you can see, there's a cost at t equals 1, A, and another cost at t equals 2, same A, and it just keeps on going for infinite amount of time. That is the simplest case that we could look at in this category. And in that case, can we find the present worth of all these uniform payments? Yeah, we know the formula for finding P given A, right? And because n happens to be approaching infinity, we take the limit of that. And earlier, I had demonstrated that in such a case, P is simply A over I. Okay, if you don't recall this formula, that's perfectly fine. But the main point is that this formula actually came from the original formula for P given A. and taking the limit of it as n approaches infinity. With a little bit of mathematical manipulation, we saw that P would be A over I. Cool. Then, what if the costs occur repeatedly at a different time than every year? Here, all these costs are occurring exactly on at t equals 1, 2, 3, 4, and so on. But sometimes what happens is something like a maintenance would be every 5 years, right? So every 10 years, something like that. And you have to incur that cost every 5 years, every 10 years, and so on. So how do we handle a situation like that? So I figured I'll make it a little mathematical. The book doesn't have this. But then I figured, yeah, I'm gonna show off my math skills and derive a formula myself. And so I said, let me show a cash flow diagram to it, and that probably will explain this. Consider a single cost that is incurred periodically at t equals m plus n, m plus 2n, m plus 3n, and so on, where n is what we call the periodicity of the payment. It's kind of like a sine wave or a cosine wave, period of 2 pi. But then you could have a phase shift. This is sort of like that. So let's see. What am I saying? Let's say there is a cost C sub m. The first time that cost occurs is at t equals m. Cool? I'm sure that you understand. But then that same cost happens after m plus n years at t equals m plus n, and a cost at m plus 2n. Oh, you mean this cost C sub m is happening every n years? Exactly, it is. And so, how do we handle something like this? All right, now check this out. Okay. So, step one would be find the present cost P sub m of this C sub m occurring at t equals m. You take this guy and find its present cost at t equals 0, t equals m thing, find its value at t equals 0. Cool. Now, when you do that, you can take the present value and smear it for n years. Okay? And we know the formula for that is P sub m equals C sub m times 1 plus I to the negative m. It's just a future cost and you are pushing it back to t equals 0. So this formula should make sense to you, right? But then step 2 is find annual cost of P sub m smeared over n years. So you take the single cost at t equals 0 and ask yourself how many equal costs over t equals 1, 2, 3, 4, all the way up to t equals n would that single P sub m equal? Does that make sense? Please absolutely make sure it makes sense. We have a cost of P sub m at t equals 0. How can you spread it out for n years? Smear it out or spread it out for n years of equal costs. So that means those costs should be at t equals 1, t equals 2, t equals 3, t equals m plus 1, all the way up to n, right? So you have a single flow of costs, a single sequence of costs occurring from 1 through n, right? Whatever is equivalent to C sub m. Okay, that we know how to do. And then we take this C sub m occurring at m plus n, find its present cost at t equals n, right? The process is exactly the same as what we did from m to 0. Here we go from m plus n to n. Do what? Take this C sub m and figure out its present value at t equals, at present value meaning at the value at t equals n, and then smear it out over the same n periods. If we do that, we will get some uniform payments here from 0 through 1 through n, and another set of uniform payments from n plus 1 to n plus 2 all the way up to this m plus n. You keep repeating the process and you have uniform payments every year all the way from 1 through infinity. That's the idea. In other words, we are converting what we see here to what we saw earlier. Let me go back to that thing. What we saw here. So now this is some payment every year occurring as for n years as n approaches infinity. And that's what we are converting this cash flow into by doing this step one and then smear it over n years. That means you take this guy and find what A would be of this present value P sub m, multiply that by I times 1 plus I to the n over 1 plus I to the n minus 1, and I'm just plugging and chugging. For P sub m, I'm plugging C sub m times 1 plus I to the negative m. And now we know that A would be the payments for every year all the way as t approaches infinity. Cool? Okay. And for capitalized cost CC of this A, capitalized cost, that means, okay, now we have a whole bunch of series of payments, at t equals 1, 2, 3, 4, all this A. What is the present worth of all of that if that happens for infinite amount of time? And go back to our original formula, A over I, and plug and chug all of this, and this looks exactly like that one, but there is a small difference. I needed to divide this A by I, right? And if you notice the formula for A, it has an I on the top. And so we are dividing by I, so I and I cancel, and that's why you see this one. So there's a slight difference between this and this. There's a times I here, but there's no times I because it got divided. Okay? All right. So this is the formula. Do you need to memorize this? I don't think so. Okay. But just uh, as long as I think you understand the procedure, what we are trying to do here, all we are doing is, hey, you got payments, periodic payments, man. So what you're doing is you're figuring out the present cost of it and then smearing it over n years. And once you do that, you have smeared out for all the way up to infinity, and I can figure out the present value of it. So that's the concept behind this. Okay. All right. Let's look at a problem so that we understand how to apply what we did. Every 10 years, the dome of the state capitol building has to be cleaned, sandblasted, and retouched. It costs $750,000 to complete the work. Using a 5% minimum attractive rate of return, what is the capitalized cost for the project? Okay. Now you can see, this makes sense. Yeah, every 10 years you would need to do some maintenance work on the state capitol building, right? Okay, so how do we do this? So the cash flow diagram for this project that extends into perpetuity, that is infinity long, is as follows. They gave this thing. If they hadn't given in the problem statement, if they hadn't given this cash flow, I would have been a little confused about, wait a minute, every 10 years, would that happen at t equals 0 or not? And I would have really, to be honest with you, I would have thought at t equals 0, we should not have had 750,000 cost because it's just starting, right? So, however, apparently this is what they meant, and I'm thankful that they gave the cash flow diagram. So the cash flow diagram does show that there is the $750,000 cost at t equals 0. I would have thought the whole cleaning process started at t equals 10, and subsequent to that at t equals 20, 30, and so on. But anyways, compare this to the one below that we derived. Now, in the last slide, we did some derivation, right? Some m and n and all kinds of things like that. So I'm showing this picture. Now, the cash flow that we have here up on the top for our problem and the cash flow diagram that I have shown here, can we compare them? Let's see. First of all, the first payment is occurring in this one where at t equals m. Where is the first payment occurring here? Oh, at t equals 0. Good. Are they the same payments every time? Yep, the same payment, $750,000. So C sub m is 750,000. M happens to be 0. Could that happen? Answer is yeah, m could be 0. That's the beauty of deriving formula for a general case like this. We could let m equal 0, right? Okay, good. And what's up with n? So that is how the periodicity of this one. How frequently is this happening? Every how many years? Oh, every 10 years. Oh, you mean n equals 10 then? The answer is yes. That's exactly what it is. And what was the formula for capitalized cost in this case? This was the formula. So, since we have the formula, first cost at m is equal to 0. First cost, where is it happening? At m equals 0. And what is the periodicity? N is 10. And periodic cost is what? C sub m? That is 750,000. I is 5%. So it looks like we know every one of these quantities and it's just a matter of plug and chug. And that's what I'm fixing to do. C sub m times 1 plus I to the negative m times 1 plus I to the n over blah blah. Oh, wait, this is 0. M is 0. What happens in that case? 1 plus I raised to negative 0. Negative 0, positive 0, they're all the same. 0 is 0, right? 1 plus I to the 0 is 1. And so let's remember that. And when you apply and use a calculator or a computer, figure it out. It turns out to be $1,942,568 and 62 cents. I like this problem. It just fairly well illustrates the situation. Cool. Next. Man, this is a little involved. If we understand this one, then we are in a really good shape. Cool. A municipality is planning on constructing a water treatment plant at an initial cost of $10 million. Every 5 years, major repairs and cleanup are required at a cost of $2 million. Every 5 years, major repairs and okay. Due to the necessity to remove sludge and make repairs, annual costs of operating the treatment plant are estimated to be $700,000, $775,000, $850,000, $925,000, and $1 million each year leading up to the 5-year major repair and cleanup. Based on a 4% per year time value of money or minimum attractive rate of return, whichever you want to call, what is the capitalized cost for the water treatment plant? Right? What is the capitalized cost? Understand this first. Capitalized cost is nothing but the present worth of all the costs. How is it different from the present worth that we did before? The way it is different is these things will last for infinite amount of time. Okay? Good. If that is the case, how do we solve this problem? Three costs contribute to this project. not three costs, I should have said. Three kinds of costs or three types of costs contribute to this project. What are they? The first kind is this initial cost of $10 million, right? The initial cost of $10 million. That's the first kind of cost. Good. We need to find the present worth. So do we do anything with this initial cost? No, it's already a cost at t equals 0. So we don't need to do any manipulation with that. It's going to be added to whatever other costs are directly. No manipulation required. However, the second one is a repair cost of $2 million once every 5 years. So now we are like, like in the previous problem, every 10 years there was a $750,000. This one is sort of like that. Every 5 years, $2 million. So that's the second kind of cost. And then operating costs are happening 1 through 5 years, 1 through 5 years respectively. First year 700,000, 775, 8, blah blah. Every different years, these are the things. And of course, the cycle keeps repeating. So this is 1, 2, 3, 4, 5 years. And on top of the fifth year is a special one. On top of this 1 million, there is a 2 million big repair one, right? So that's happening at t equals 5. And then at t equals 6, what's happening? You go back to this guy, 700,000 at t equals 7. Whatever was at t equals 2 is the same at t equals 7, 2 plus 5, period is 5 years, and so on. So this is at 6, 7, 8, 9, and 10. And at 10, you also have to add this 2 million. That is the scenario, right? So what do we do? Well, only costs 2 and 3 are recurring costs occurring every 5 years, right? To find the capitalized cost of this, we will first find the present cost of 2 and 3. Okay, in just one period, what is the present cost of 5 years? What is the present cost of this 2 million at 5 years? What's the present cost of 700, 775, all of this at t equals 0, right? And then we will find the equivalent annual cost of the present cost by smearing it over 5 years. And then we'll find the 5-year smeared equal cost. And then we know from that those are the annual costs that will not only go on from 1 through 5 years, but also from 6 through 10 and 11 through 15 and so on. So that will keep on going for infinity. That's the strategy. As long as you understand that, man, you're in a good shape. So P sub A is, first, what am I doing? I'm taking this $2 million guy and projecting him back all the way to t equals 0. It's happening at t equals 5. So I'm asking, what is its value at t equals 0? And we know the good old formula. And then I need to take this 700,000 and move it back by 1 year. So this is happening at t equals 1. So I want to know what its value is at t equals 0. So I'm pushing it back to t equals 0 with this formula. And then, would you agree? We need to do the same thing with t equals 2. This 775 times 1 plus 0.04 to the negative 2. Okay, so plus 850, but needs to go back by 3 years, and plus dot dot dot, plus this fourth guy and this fifth guy and all of that. Okay, plus dot dot dot, I simply did that because I recognized, you know what, every one of them I can factor out 1,000, right? This has I can factor out 1,000 out of this, 1,000 out of this, and every one of them. So I did that. And so then what happens? I don't need to write such big long numbers. That's the whole idea. 1,000 times 2000 times 1.04 to the negative 5, 700 times 1.04 to the negative 1, 775, 850, and then there is this 925,000. So I do have that here. And finally, this 1 million, if you factor out 1,000 out of that, you get 1,000. And when you add all of these up, it turns out to be $5,401,730.09. Okay, so what is this now? What is this 5 million number? It is just the present cost of one cycle of costs. Okay, one cycle from 1 through 5, whatever the costs are. So that one is this 5,401. Now, what are we going to do? We will find what the smeared out cost is. If we take this guy and smear it out over 5 years, what would be the equal cost? And so that is what I'm calling A, equal cost. And for that, we'll apply the formula that we had before. That is, take that present value and multiply that by I times 1 plus I to the n over this thing. And so I happens to be 4%, so 0.04. And 1 plus I, all of this. N is 5. Plug and chug. And ladies and gentlemen, that turns out to be, I didn't figure out what that number is. I was like, why in the world I didn't figure out how much that is? That is because I'm waiting. I'm waiting so that this capitalized cost of this uniform cost is A over I, right? Once you have this for infinite period, every year all the way to infinity, then we can divide that by I in order to find the present cost of that, present value of it. And so we end up with P sub A times 1 plus I to the n over this thing. In the sense, this I cancels out. And that is going to be this. This I'm sure I figured out. And ladies and gentlemen, that turns out to be $30,334,375.95. Right? So is that the total capitalized cost? Have we done everything? No, no, no. This is only the present cost of these recurring costs, the cost 2 and 3. But there is also this initial cost of 10 million. Let's not forget to add that guy. So CC, the capitalized cost, is that initial 10 million plus these distributed costs of 30 million and a total of 40 million. Ladies and gentlemen, that's the right answer for this one. I hope this one made sense, right? Cool. One last problem, in fact, I think. A generous benefactor donates $500,000 to a state university. Why don't you give it to Tech, man? The donation is to be used to fund student scholarships. If the state university earns 4% per year on its investments, determine the dollar amount of scholarships that can be awarded each year if the donation is to last 20 years, 30 years, 50 years, and forever. Aha, that's a nice one. You know, I was thinking, I was walking just a while ago, and I was thinking about this problem, and then it occurred to me, man, something like this must have happened with the Nobel Prize also. So they give out the Nobel Prize every 4 years, right? And now, of course, there are many more categories, and it's possible that, say, for instance, the one in physics, Nobel Prize for physics, could be earned by four different people, and they pay $1 million for each of the recipients in that case. Okay, uh, and man, I would love to Sit down and get some numbers on that. How much must Alfred Nobel have contributed to this Nobel Prize? I wondered. So, but anyway, that cost is fairly straightforward. Um, and we don't know the I value for the Nobel. Like, what is their minimum attractive rate of return? We don't know that. We can estimate, of course. Anyways, so what are we talking about? So, finding how much scholarship, dollar amount of scholarship that can be given each year. That's basically finding A. Given what? Given this P. That's the initial amount of endowment money that the state university has. So we know P and I is known. And then N is different for different A, B, C, D. For A, it's 20 years, 30 years, and 50 years, and so on. So it's just a matter of, ladies and gentlemen, just plug and chug, right? N equals 20 for this, so that's the one. And that turns out to be $36,000, 790 cents and 88, $36,790 and 88 cents. And for 30 years, it'll come down to 28,915. And for if we were to extend it to 50 years, then each year the scholarship amount that can be awarded goes down a little more, 23. But if you want for it to last forever, simple. We said P was A over I, so A is P times I, as simple as that. And so that turns out to be $20,000. So once the university gets $500,000, then they can give $20,000 every year forever with that $500,000, assuming that the state university earns 4% per year on its investments. Cool. Alrighty. Amigos y amigas. Adios.